Alrighty, welcome to the physics video on thermodynamics. We are moving on from the original energy we started with, which had three types: gravitational potential energy, spring potential energy, and kinetic energy. And now we're going to extend that and learn about two more types of energy. One of them is thermal energy, and one of them is bond energy. So those two combined form the physics topic called thermodynamics. And this is chapter 12 in your textbook. Alright, thermal energy is very exciting stuff. It has to do with temperature, what things called thermal equilibrium, conversion factors, so converting between Celsius, Kelvin, and Fahrenheit temperature scales, learning how heat flows, specific heat, and total heat capacity for objects. We'll go through each of these topics kind of one by one with various slides and pictures. So the first thing is this new type of energy, thermal energy. So thermal energy is our fourth type of energy. And its indicator, remember all the different types of energy we learned so far have indicators that tell you whether or not that type of energy is involved in the problem. The indicator for thermal energy is the temperature of the object. So the way that you can tell an object has gained or lost thermal energy is by seeing if the temperature of the object has increased or decreased. So what is it that's actually happening on a small scale, though, within the object when it's gaining or losing thermal energy is the actual individual particles. They're moving faster or slower. So the hotter something is, the actual individual particles inside of that material are vibrating or zipping around, if it's a gas or a liquid, zipping around at much higher speeds. And if it's colder, they're vibrating less and or zipping around at much slower speeds. So temperature is a measure of the internal energy, and thermal energy is the type of energy that it is. So temperature is the indicator, thermal energy is the type of energy, and what it actually is the energy of the internal random molecular motion. So either vibrations or particles zipping around at a microscopic scale. The formula will be coming up soon, but I want you to get a kind of conceptual understanding first. Alright, so thermal equilibrium and temperatures. Thermal equilibrium is kind of like a vocabulary word that means that the different constituent parts of your system are all at the same temperature or settled at stable values such that the temperature is not changing. Anytime things are changing, it's not in equilibrium. So equilibrium is when everything is at a stable value. So typically that means everything in your problem is at the same temperature. Because otherwise heat would be flowing from one to the other to change that temperature. So how do we measure this temperature that we're talking about? There's three different ways to do it. One is Celsius, one is Fahrenheit, and one is Kelvin. Fahrenheit is what we're most familiar with in America. Celsius is what most of the rest of the world uses. And then Kelvin is the scale that we use in science. And the reason we use Kelvin in science and for thermal energy is because you need a set starting point for all of your energies, and it's reasonable to choose a starting point as the lowest possible temperature. So if you guys have heard of absolute zero, maybe in chemistry or in another class, the Kelvin scale starts at absolute zero, whereas the Celsius scale starts with its zero at the freezing point of water, which in the olden days, before they understood more about thermal energy and max and minimum temperatures, then setting that at zero as the temperature where water freezes was a reasonable thing because that was an easy thing to observe. It was an everyday point where there was a main transition. But you can have negative temperatures on the Celsius scale. You can have ice at 0 degrees Celsius, but you could also have ice at -5 or -10 or -100. And so it's not that convenient to have negative thermal energies because the object, even if it's ice, it still has some energy by virtue of its molecular motion and vibrations of its internal molecules. So the way that you can convert between these temperatures are given by these three equations. If you have the temperature in Fahrenheit, TF, and you want the temperature in Celsius, you first subtract 32, and then you multiply by 5/9. To do the other way, you do it in the opposite order, so just solve this equation for TF. First multiply by 9/5, that is the opposite of multiplying by 5/9, and then add 32. So these two formulas will take you back and forth between Fahrenheit and Celsius. To get back and forth between Celsius and Kelvin, it's a straight swap. Plus 273 to the Celsius temperature gives you the Kelvin temperature. So I got a picture to help kind of visualize what's going on. So the water freezes at 0 degrees Celsius. So on the Celsius scale, water freezes at 0 and boils at 100. So that's how this Celsius scale was created, was to make the transitions of water the main point of the numerical values. And then it just so happens that you can go down all the way to negative 273 on the Celsius scale, negative 273, and that is absolute zero. That is the coldest that you can get. And if you want to talk about absolute zero, I'm happy to do so in office hours. It's a really cool topic. So negative 273 is the coldest you can get on the Celsius scale. So the Kelvin scale just takes all of these numbers and shifts them up by 273 units, so that the 0 on the Kelvin scale is actually absolute zero, and then all temperatures here are positive. So the freezing point of water is now 273. It's actually 0.15, so this should be 273.15 negative. The shift is 273.15, but if you round to 273, that's fine. And then the boiling point 100 degrees higher in Celsius is also 100 degrees higher in Kelvin. So Kelvin to Celsius is simply add or subtract 273 to go back and forth. Fahrenheit is all screwed up. The reason Fahrenheit is all screwed up is because the size of 1 degree is not the same on the Fahrenheit scale or the Celsius scale. So 1 degree Celsius, a change of 1 degree Celsius is equal to a change of 1.8 degrees Fahrenheit. So a Fahrenheit, the unit of a Fahrenheit, is a smaller sized unit than Celsius, and there's a 32 degree offset. That's why there's two conversion factors. One is you have to multiply by 5/9 or 9/5, and the other is you have to add or subtract 32 when you're going back and forth between the two. So we'll try to avoid Fahrenheit as much as possible, and we'll try to use Celsius and Kelvin. My only warning for you is that when you're measuring temperatures or getting answers out, you're probably, common sense will tell you the answer in Fahrenheit. So if you get a temperature out of like 120 Celsius, you may not realize that that's really, really hot. So if it's like the temperature outside on a Saturday afternoon and you get 120 Celsius, or even if you get 80 Celsius, that's way, way, way too hot. Whereas if you got 80 degrees Fahrenheit, you'd be like, okay, that's a reasonable answer. So just think about the different values. Try to not memorize them, but have a good understanding of what reasonable values are. For example, room temperature is around 70 degrees Fahrenheit, which is around 20 to 22 degrees Celsius, which is around 293 degrees Kelvin, or 293 Kelvin. Funny little story here is, when you're talking about Fahrenheit and Celsius, you say degrees Fahrenheit and degrees Celsius, but when you're talking about kelvins, you don't say degrees Kelvin, you just say the number and then Kelvin. And honestly, I don't know why that is, but it's not a degree, it's just a straight up unit. So just Kelvin. Okay, now we're getting into the nitty gritty of how this energy is transferred back and forth, where one object will gain the thermal energy and another object will lose the thermal energy. Up until now, the only way that we learned that heat could be, or that energy could be transferred, was via work. And remember, work was force times distance, and so that was one way that you could transfer energy. And now we're introducing a second way that you can transfer energy. So heat flow is what it's called, transfer of heat by heat flow, and the book uses the variable Q. I don't know why particularly, except that H is often used for enthalpy, which is something different that we can talk about later. So the variable H is kind of taken up, so they use Q to represent heat flow. So just like work causes a change in energy, heat flow also causes a change in energy. So heat flows, which means energy is transferred from one object to another, and there are actually three different mechanisms that thermal energy or heat flow can occur. So the first is called conduction. This is direct contact between two objects. So if you take something hot and something cold and you touch them together, energy will transfer from the hot object into the cold object. That is through conduction or direct contact. Okay, the second one is called convection. Some of you may have heard of a convection oven. Heat is carried by moving particles, which are oftentimes air or water, but could be something else. So convection currents are something like you blow hot air on something. So you've got your heat source, and then you've got these moving particles which carry that energy from the heat source over to the object that you're trying to heat up. So it's kind of like direct contact because the air particles themselves are in direct contact with the object, but the heat source and the thing that's getting heated up are not in direct contact. There's a medium in between them of some kind of moving particles, air or water. So you might have heard convection currents in the ocean, thermal inclines, etc., that cause water to flow and carry cold water down from the north into the middle, or warm water from the middle near the equator out into the Gulfs, or into the North and South Pole. The third mechanism by which heat can flow is called radiation, and this is electromagnetic waves. So anytime you stand outside and you put your arm in the sunlight and it feels warm, your arm is being heated because it's being hit by electromagnetic radiation, which transfers energy into your arm in the form of heat. And we're going to talk about that a lot, but not until the second semester when we learn about electricity and magnetism. So for now, we'll just know that it's a method to transfer energy, but not very much about how it works. So again, work is one way to transfer energy, and now heat flow is a second way to transfer energy. Okay? Specific heat, this is something interesting about objects. So you know that when you transfer energy to an object, thermal energy, its temperature will go up. But exactly how much will the temperature go up based on how much energy you transferred? It depends on what the object is. Some objects are very easy to heat up. Some objects are very difficult to heat up. So if you add 100 joules of energy to object A and 100 joules of energy to object B, they may not both go up by the same actual temperature. Maybe one goes up by 1 degree and one shoots up by 10 or 15 degrees. So there's some kind of properties of the object themselves that determines the relationship between the actual temperature and the amount of energy that you're adding or subtracting. So let's think about what kind of things it depends on. Certainly it depends on how big the object is, right? If you add 100 joules of energy to a tiny little object, or you add that same amount of energy to something really big, you expect the smaller the object is, the more dramatic its temperature will go up. I think that should be common sense, but just think about a frying pan. You put a giant-ass frying pan, cast iron skillet on the stove, or you put a tiny little tin pan on the stove. The tin pan's going to heat up faster than the skillet because it's so much smaller. Okay, the second is the amount of thermal energy gained. Okay, if you put one burner on high and one burner on low, obviously you're transferring more energy with the high burner, and so that object will heat up faster. But finally, and one that's a little less maybe intuitive, but if you think about it, you should be able to think of some examples in your life, which is the type of material. So maybe on the one hand, you've got a bronze skillet, and on the other hand, you've got an aluminum skillet. I don't know if you know, but different skillets cost different amounts. And it has a lot to do with how they heat up, how these different materials change temperature when you add energy to them. And some are better for cooking, and some are not better for cooking. But certainly the type of material affects how hot or how quickly something will heat up. So there's this thing called a specific heat, and there's a different value for each material. The lowercase c, or in the textbook they use uppercase c, but I like lowercase c, and we'll talk about it in class Y, is called a specific heat. And in your textbook, you should check page 318. It's got a list of specific heat values for lots of different materials. Okay. So the equation is as follows. The change in thermal energy, so this is going to be measured in joules, is equal to the mass of the object times the specific heat of the object based on its material times the change in temperature. Okay? So the heavier it is, the higher its specific heat, and the more the temperature changes, the more energy you must have added, or if the temperature went down, the more energy you must have subtracted. So notice there's a delta here and a delta here. Okay? If you add or subtract thermal energy from an object, its temperature will change. If you take away the delta and you take away the delta here, you just get E therm equals mCT. This equation is only valid if the temperature is measured in kelvins. Okay, so we just said the reason the Kelvin scale is so useful is because it starts at absolute zero. If something has a temperature of absolute zero, if you plug in T equals 0 right here, it has no thermal energy. And any other temperature higher than that, it will have thermal energy. So if you were using Fahrenheit or Celsius, you might have a negative value of temperature, and it wouldn't make sense to have negative thermal energy. I mean, it still has some energy in there. The molecules are vibrating, they have energy, so it makes sense to have a positive value. However, if you're looking at a change in energy here and a change in temperature here, you can actually use Celsius or Kelvin. The reason is because the size of 1 degree Celsius is the same as the size of 1 degree Kelvin. So if you add 273 to the temperature in Kelvin before, and you add 273 to the temperature in Kelvin after, they both went up or down by the same amount, so that delta T in Celsius and delta T in Kelvin are the same physical size. So say you went from 0 to 10 on Celsius, that'd be the same as going from 273 to 283 in Kelvin. And the change in temperature once you subtracted them would be the same no matter what. So again, here's a very, very, very important formula. Thermal energy is your type of energy. Temperature is your indicator, and it depends on the mass and the specific heat as well. Okay, total heat capacity. I'm not sure this is even in the book, and it's not, in my opinion, all that useful, but I just want to mention it so that you understand what it is. This formula we just had, let me go back one slide. This formula right here, mc delta T, this specific heat depends on the type of material you'll have, but you have to multiply it by how much you have. So if you multiply how much you have times the type of material, that gives you an actual object, okay? And so a lot of times if you have a physical object, you want to just calculate what's called the total heat capacity of that particular specific object. So if you multiply the mass times the specific heat for whatever material it is, it'll give you the total heat capacity of that object. And so you can rewrite the formula as change in thermal energy equals the heat capacity of that object times the change in temperature. So the higher the heat capacity, the lower or the less its temperature will fluctuate. So if you have some kind of material with a really, really high heat capacity, it means it takes a lot of energy to put into it before it will actually exhibit a much noticeable change in temperature. If you have something with a low heat capacity, if you decrease this variable, then you're going to increase the temperature, and it will heat or cool quickly. Okay, so you don't need to know this very much. You can always just use E therm equals mc delta T, but I wanted to mention that if you have an entire object and they give you the total heat capacity for the object, that's the combination of m and c together to give you the total heat capacity. Just a secondary reminder, this is really important. Our textbook uses capital C to represent specific heat, and I personally use lowercase c for specific heat and capital C for total heat capacity. Every book I've ever seen does it the way I do it, and our book is one exception, so I apologize. But again, I don't think you need to worry about total heat capacity, so pretty much anytime you see a C, you can use it as specific heat if you're following along with the textbook. Okay, take a break. I know you've just covered quite a bit of material. You probably paused it and took good notes. Go run around, watch a movie, play video games, etc., and come back after you've given your time a small amount of time to rest. Alright, hopefully you took yourself a break. Welcome back to the second part of Chapter 12. This one is about more laws of thermodynamics, and specifically about the change of state of objects. So you learned about the states of matter: gas, liquid, solid, and maybe even plasma. And we're going to now talk about the energy changes when you go from one state to another. Alright. There's also a cool demo we're going to do in class, so remind me to do the demo with ice cubes melting on different blocks. It's actually pretty cool. I mean, it's simple, but it's really interesting results. Alright, so with that in the back of our minds, changes of state. Okay, bond energy. So we've learned 4 types of energy up until now. We're adding our 5th type of energy, which is bond energy. So think about what happens when you are boiling water. You start adding energy to the water, and the temperature starts to go up. Okay, but at some point, the temperature stops going up, and something else happens. So even though we're still adding energy to it, the energy is no longer going into thermal energy because the temperature doesn't keep going up. Yet that energy has to go somewhere. So you might ponder, okay, well, where's that energy going? So it turns out what happens when water starts to boil, it's changing state from a liquid into a gas. And in order to do that, you have to break the bonds that are binding those liquid molecules together so that they can escape into the gaseous form. So what's happening to this energy is, as it goes in, it's going into breaking the bonds rather than increasing the thermal energy. So this is our 5th energy type. It's bond energy. And when you break or form bonds, there are energy changes. When you form a bond, energy is released. When you break a bond, it takes energy to do that. Okay? And how can you tell that bond energy is involved in your problem? Of course, there's going to be an indicator. Phase transition. So anytime you have either all of the object or part of the object undergoing a phase transition, that means either melting, vaporizing, solidifying, or condensing, those are the 4 phase transitions, then you're going to have some kind of bond energy in your problem because you're having a change of state. Okay? Melting and boiling. So anytime something is transitioning between the solid and liquid transition, so either going from solid to liquid, which is melting, or going from liquid to solid, which is called solidifying, that is called fusion, because the molecules are fusing together or breaking apart from unfusing, I guess. So the formula that you can use to find out how much energy it takes to melt something, or how much energy is released when it fuses back together, it's delta E equals m times h sub f. So m is the mass. The more of the object that you have, the more energy it takes. And then hf is again a constant, kind of like specific heat, but now it's a constant that tells you how much energy it takes to melt a particular type of object. So each different type of material will have a different value for the heat of fusion. And in your book, page 324, you can see a list of all those heats of fusion. So it's constant for a given material, and the mass times the heat of fusion tells you the total energy. So the units for heat of fusion are like joules per kilogram. So when you multiply by the amount of the object you have, it tells you how many joules it takes to melt it. Okay. The liquid-gas transition is the same formula because it's still a change of phase. It doesn't matter which phase you're undergoing the phase change through. You're still undergoing a phase change, so the formula is the same. But the constant for vaporization or condensation, H sub V, is going to be a different numerical value than H sub F. So if you take the same substance, say liquid water, it takes a different amount to break the bonds between liquid water and solid water being ice. So that phase transition takes a different amount of energy than the transition of liquid water to gaseous water or to water vapor. So even though it's water in both cases, and even though it's a phase change in both cases, the amount of energy taken to break the liquid-solid transition is different than the amount of energy taken to break the liquid-gas transition. And in class, I want to have a whole class discussion about why that is. So maybe now think about, why does it take different amounts? Which one do you think takes more? And then maybe look in your book on page 324 and check and see if you're right, and come to class prepared to discuss that. Okay, so we've learned about thermal energy, the random molecular vibrations, and we've learned about bond energy, breaking and forming bonds. Couple that with everything we already knew about work being done to transfer kinetic energy, gravitational potential energy, and spring potential energy, and you can combine all 5 of these together into what is called the First Law of Thermodynamics. So the total energy has to be conserved, but now there's 2 ways to transfer it. You've got work and you've got heat, and we can combine those together into one law. So here's the equation. The total change in energy is equal to Q minus W. Now, you might be wondering, why isn't it Q plus W? It's a fantastic question. For some odd reason, Q, the heat flow, is defined to be positive when heat is added to the system. Okay, that seems pretty reasonable. That makes sense to me. So if Q is positive, the energy goes up. It's gained energy. However, work is defined as positive when work is done by the system. Okay, so but when work is done by the system, it's losing energy. It's transferring that energy to something else, whatever it's doing the work on. So in this case, if the object does work on something, the total energy has to go down because the object did work on something else. It lost energy. Hence this minus sign right here. So it's not very convenient. Personally, I don't even like to remember this formula. I just like to know in my head, hey, there's 2 ways to transfer energy. I could do work, or I could transfer it via heat flow. And I know if my object did work on something else, my object lost energy. And if something else did work on my object, then my object gained energy. And if heat flowed into my object, it gained energy. And if heat flowed out of my object, it lost energy. And I can keep track of the positive and the negative signs just using that kind of logic. So I would encourage you to do the same and not try to memorize this formula and plug stuff in, but just actually use your conceptual understanding of which way the energy is going to decide whether it should be positive or negative. Okay, a heat engine is our next topic, and we're almost finished, so don't freak out too much. A heat engine is a way to kind of examine the relationship between work and heat, and it's a way to take advantage of one and get out the other one. So for a cyclic process, an example is a car engine, the final state is the same as the initial state. So after your cylinders go through one full cycle, the gas gets injected, it gets blown up, the pistons fire, the car moves forward a little bit. At the end of that whole cycle, you're right back where you started at. And so the total energy at the end has to equal the total energy at the beginning. Okay, so that means whatever energy goes in has to come back out somehow. Okay, so now if you look at how it actually operates, you've got energy coming in from some hot area. That's the actual ignition of the gas in the cylinder. So that blows up, creating a lot of heat. Okay? Then what happens is that expands the piston. Well, that's a force over some distance, right? So that means work is being done as the piston expands. Okay? And then what happens is you eject out the exhaust. So whatever energy you gain coming in, some of it is going to come out as work. Some of it is going to come out as thermal energy. The total work out plus the total thermal energy out has to equal the total thermal energy in. Total energy in has to equal total energy out because the change in energy in one cycle is 0. So whatever energy comes in has to come back out. Here's a nice little example. If you input heat by burning a fire, you can put water above it, and that water will boil, creating steam, and the steam can push a piston, and the piston can rotate a wheel. So this is an example of a steam engine. This is just a generic engine of any type. You've got some way to get the heat, you've got some way to get the work, and then you've got some exhaust heat. Okay, so the idea of an engine typically is to get the most work out possible. You want to maximize the work out. So ideally, if you put in 100 units of heat, you'd get out 100 units of work and 0 units of heat coming out. But there are constraints when you're actually physically creating these devices, and you want to maximize this, but there are things that you can't help. So we'll talk about heat engines in class if you want, or in office hours. But you can define the efficiency of any engine by looking at the work out divided by the heat in. So for every 100 units of heat that you plug in, how much units of work do you get out? So say it's 50% efficient, half of the energy you put in is useful and converted to work. The other half is essentially wasted. So we would all love 100% efficiency, but of course that's not the case. And you can look at different types of energy usage and look at their efficiencies. Like, for example, an electric car, a gasoline car, a coal power plant. All of these things are trying to convert thermal energy into work, and they all have different efficiencies. Okay. Next topic is, why are some events one way only? So this is a little bit of a change of gears, but suppose you've been paying close attention for the past maybe 3 chapters. You're starting to notice that we do a lot of looking at the before and after, and we do a lot of comparing the energy at the beginning to the energy at the end. And there's nothing that would ever prevent us from switching what the starting and the ending points were. Like, say you have a ball up in the air and you drop it. Okay, it started with potential energy of gravity, it falls down, and it now has kinetic energy because it's moving. And when you drop the ball, it always falls down. You can never naturally, without you putting some kind of force on something, you can never do the reverse. You never have a ball on the ground spontaneously fly up into the air and exchange one type of energy for the other type of energy. And so you may wonder, what controls in which direction these energy changes happen? Why does gravitational potential energy go to kinetic, but not the other way around spontaneously? And so the way that we can do that is by looking at this new variable called entropy. So you've probably heard of entropy, maybe in 8th grade science or just throughout other science classes, maybe chemistry. And we're not going to talk about it in too much detail, but I just want to give you a taste of what's going on. So this new topic, entropy, has to do with probability and statistics. Okay, when one object gains energy, okay, all the particles vibrate a little bit more. So you've got some object, all the particles are vibrating, you add energy to it, now they're all vibrating a little bit more. Okay, and the more vibrations they have, the more disordered they are, the more different possible ways that they can be arranged. Imagine your room, and then if you shake it very gently, things are kind of going to get dislodged, get a little bit messy, and then take it and then shake it vigorously. Things are going to go flying all over the place, and it will become very disordered. So the more energy you add to something, the more things are bouncing around, the more disordered they become. There's more possible ways they can be arranged, and it's less likely that they're going to be in a nice organized state. So our equation for entropy is the change in entropy equals the heat flow divided by the temperature. Okay, ignore this equation for now. I'm not decided yet if we're going to use the equation, probably just for the math students, and I'll do a little special thing in class. So for now, ignore this. What you do need to know is that the second law of thermodynamics states that natural processes tend to increase the total entropy in the world. So we know the energy at the beginning equals the energy at the end. Okay, but in one direction, the entropy will increase. In the other direction, the entropy will decrease. So how do we tell which is initial and which is final? Whichever direction the entropy arrow points tells us which way things will happen in nature. Okay, the way that you can figure this out is by using probability. So when one object gains energy, it's going to lose order, and when the other object loses energy, it's going to gain order. However, the amount of order gained by the one that got more ordered is not as much as the amount of order lost or disorder gained by the other one. So, okay, entropy has to do with probability. The more probable something is, the more likely it is to happen. And when you add energy to something, the energy goes up, the randomness of the particles goes up, and therefore the entropy goes up. So when energy is transferred from one object to another object, entropy is also transferred. The more energy something has, the more entropy it gains. But the amount of entropy it gains is relative to its temperature. So if something is very cold and very ordered, it's just not vibrating very much, and you add some energy to it, it's going to get quite disordered. But if something is already super, super hot and everything is just flying all over the place, and you add some more energy to that, I mean, it's already so disordered that it's almost not noticeable that you've added more disorder to it. So whether it's currently hot or cold, the energy that's added has a different effect on the amount of disorder in the system. Adding disorder to something cold has a bigger impact than adding energy to something that's already hot. So all of that combines to lead to this idea that energy transfers from hot to cold increase the disorder of the cold thing a lot more than they decrease the order of the hot thing. And so the net increase in entropy here is big, and the net decrease in entropy here is small. So overall, the entropy increased by transferring energy from something hot to something cold. Okay, think about what's likely to happen. If you have a deck of cards, you could put them in order 2 through ace of each suit, and you could shuffle them 100 times and then check. And it's possible that they'll be in that exact same order, right? I mean, mathematically, there's one chance out of how many millions of chances that could happen. But there's so many other ways that they could be disordered and not in the order that you wanted, all mixed up, that whatever is most likely to happen is what you notice. And remember, a deck of cards only has 52 cards. The world, you know, a 1 mole of gas has billions. Think about 1 mole, right? Billions upon billions upon billions of particles. What's the probability that all of them are going to arrange up in this nice exact way? It's technically possible, but mathematically pretty much never going to happen. And this is, again, some math that we can do in class on the board to just show your mind exactly how unlikely it is for things to go from a disordered state into an ordered state spontaneously. Not impossible, but so unlikely that essentially it never happens in the natural world. All right, my goodness, what a beast this chapter was. Let's summarize very, very quickly. Section 12.1, most important things are thermal energy is your new energy type, its indicator is temperature, and its equation is change in thermal energy is m, mass, times c, specific heat, times delta T, the change in temperature, and the temperature needs to be measured in Kelvin if it's the actual temperature, and Celsius or Kelvin if you're looking at a change in temperature. Number 2, bond energy. You can tell bond energy is present by looking at changes in state. That means liquid to gas, or liquid to solid, or sublimation. I guess it could go gas straight to solid. Anytime the state changes, then you're going to have bond energy, and your formula is change in bond energy is mH, where m is the mass and h is the heat of vaporization or the heat of melting, which you can look up in the tables on page 318 and 324. Everything else is cool and fun and interesting, but the bond energy and the thermal energy are by far the 2 most important topics from this chapter, so spend the majority of your time understanding those things. And we'll review all this stuff in class.